but I'm going to go ahead and get rolling here. I realize that we have potentially some remote participants, so I want to welcome them to this also. So this is the next in our series of seminars that have been pretty interesting, and I really like this one myself. So today we're going to have Bertram Ludäscher, who is a professor over in Gislis on campus here. But how recently did you arrive? Is it just in August? Okay, so I knew it was quite recently. Prior to that, he was in California, most recently at University of California, Davis, and he was focusing on activities with respect to life cycle, or full data life cycle, and the use of workflows. I don't know if his bio was circulated with the talk information, but he's one of the folks that founded the Kepler workflow, and he's had a particular interest in provenance and curation and automating that through the workflows, which I find a pretty interesting topic, particularly with our recent focus on data activities here at the center. Connecting that to the workflow, which I think is the way to make these things a bit easier for most researchers, is a really interesting mechanism. He's also works with the Data One project as a member of the leadership there, focusing on data and workflow provenance there. Prior to that, he was at SDSC, our friends there at San Diego. And he was an adjunct faculty at the CSC department at UC San Diego. As training, he got in Germany at both Technical University of Karlsruhe, which I think is a beautiful campus, actually. I've been there. And his PhD from University of Freiburg. So welcome to Bertram.
Thank you, John, for the introduction. All right, it's a pleasure to be here at NCSA. My home department, as was already mentioned, is Gislis. But I also have affiliations with NCSA and the Department of Computer Science, and I'm looking forward to sort of work at the intersection of all of these. So let me first give an outline. Since I'm new to campus, I thought it might be also a good idea to talk a little bit about myself briefly. So where I'm coming from, so my own provenance. There's some strange loops in life. You probably found those in your own lives as well. So I'll point some of them out. Then the main topic really of the talk is how do you go from data to knowledge? That's sort of a slogan that's popular, has been popular for many years, but now made it into funding announcements and things like that. Using scientific workflows, which I think of as cyber infrastructure upperware, because there's all this stuff down there, but at some point the user needs to interact with the tools, and scientific workflows are such a mechanism. Then I'll also talk about a particular research interest of mine, which is provenance. It's not really the underwear of cyber infrastructure, but it would be located nearby, and I'll say more what I mean by that. And then I have a broad range really of research interests and projects I'm working on and interested in, and I will probably run out of time towards the end, and I have two other talks that are not overlapping a lot. So if you like what you see today, you might like these other talks as well, but they're very different. One is at the SIRS seminar at Gislis. This will be about reasoning about taxonomies. And then I'm also speaking at the database group at computer science on first-order provenance games. Really sounds all disconnected, but it isn't. But it takes a while to notice that. So first, a little personal provenance. So I studied computer science at the University of Karlsruhe, and then a couple of years ago found out that it no longer exists, which is not nice when your alma mater goes away. But it turned out to be really a naming issue. The university is doing fine, thank you very much. It's just called by a different name now, and sort of like Deus Ex Machina, it came from Technical University of Karlsruhe. It became the Karlsruhe Institute of Technology, aping a little bit the American friends. The Germans always like to look across the Atlantic for inspiration. Sometimes people look back, it goes both ways. So that still exists, and an interesting sort of personal history there. I started as an undergraduate a very long time ago on a project called Hector, Heterogeneous Computers Together. It was a collaboration between IBM Germany and the University of Karlsruhe at the time, and what they developed was DACNOS, a distributed academic network operating system. Now that sounds familiar, there's a shorter word for that. You could call it a grid, if you like to. So sort of an early prototype. So I was involved in particular with the upperware, as I like to call it, the task setup service. I was just a student helper, really. I didn't have any major role in that. But looking back at this, I recently dug up some references, and so these for me are some sort of sacred scrolls now. So this was my advisor, Cora Förster, and if you look at what she did there, it was basically workflows, where you're having a distributed environment, and on top of which you were trying to stitch together an application. So I thought that was rather interesting. So in some sense, sort of predating notions such as the grid or scientific workflow. So this is a theme that you'll see a couple of times. All this happened before, and it will happen again. Some of you might know where this comes from. So I thought in the beginning it was a little bit too much C hacking, and then I went on to artificial intelligence and logic. I thought, workflows are boring, databases are really boring. It's sort of an irony because I became a professor of databases then in Davis later. So I was working on more logic things, and there's again a connection that hopefully will become apparent eventually. So I got my diploma from Karlsruhe. I did work on theory improving, and in theory improving, what you do is you try to give evidence why a certain fact is true, and it is something that's very relevant nowadays, again in database theory, in the area of what's now called provenance. So you want to give evidence. So this is at the very technical level. But I also always like to work with systems. So in fact, in my master's thesis, then I also generated some assembly code. It was back in the day, it was 86 or something close to it. That would sort of run faster to do these reasoning steps. Okay. Then so onto logic and databases. I got my PhD in Freiburg, which is also a very nice campus in the Black Forest. A lovely area. I highly recommend. Visit Germany when you can. And I worked there on databases, logic databases, and something I felt at the time was a little bit esoteric and not very practical. Like, data log, deductive databases was already on the decline in the cycle, and why does my advisor give me this topic to work on? But it worked out all right, and indeed, a few years ago, happened again. There was some sort of back to the future moment because data log has become popular again in both in academia and industry. There's sort of a workshop. Workshops were held on this data log 2.0. Sort of a well-known database colleague, Joe Hellerstein from Berkeley, gave a keynote at a theory conference. Said, "Oh, we were wrong," because he and Stonebreaker, I think they had given a sort of rather critical comment on this polishing the round ball. Why are people doing this sort of theoretical research in databases? And sort of, only 10 or how many years later he came back to it himself. There's companies that do very well having sort of powerful data log engines under the hood and doing some really serious stuff. A former colleague from UC Davis, T.J. Green, for example, works for this company, and as well as a former PhD student of mine. So they have been a little bit of a brain drain to academia. They do fun stuff, and people like to work for them. After my PhD, I went then to San Diego, La Jolla, very nice campus too. I was there until 2004 in the Supercomputer Center and CSE department. I working with Regan Moore with National Archives projects, digital library projects, did some data integration research, and during that time, we also started the Kepler workflow system. We got a head start, a very big head start, both because we started from open source software. Now that's important nowadays. Was important then. So we used the Ptolemy 2 system from Edward Lee at Berkeley, which was really originally meant for something else, for the modeling and simulating complex computational models and analyzing them, but we thought that's a great start. I personally felt that other than the software, it's really the research that they've done. This is something that's underexplored. They have done very nice research. There's lots of PhD thesis papers coming out of that, and we can learn, in fact, from their research and apply that to scientific data management. That is potential that has not fully been used. I like naming things, so during those times, this gives sort of a flavor of what I've been working on. I've worked on data integration, mediation of information using XML. So this was a mixed prototype, barbecue, blended browsing and querying, something that's, if the weather was nicer, we could do today. I worked also with the BERN project, Bioinformatics Research Network at the time in San Diego, led by Mark Ellisman, and we developed a knowledge-based information integration system for neuroscience data. So I named that KIND. And also Kepler, was an idea after Ptolemy. Of course, we wanted to call it first Copernicus, but I found out that name was taken, and I'm glad it was taken. It's not so easily over the lips than Kepler, and a couple of other things. So the genesis really of Kepler is two projects that I was involved with, the SEEK project, Science Environment for Ecological Knowledge, and then the DOE project, the Scientific Data Management Center. And that really helped sort of start this, this project. Okay. And finally, from Southern California to Northern California, we're coming closer, and then now to the Midwest. So for the last 10 years, I've been at UC Davis, and first at the Genome Center, and then also at another building there. And so for the remainder of the time, I think I should step forward. I'll talk about sort of the current research efforts and ongoing activities. Now, this is by now sort of an old slide, the fourth paradigm. Jim Gray many years ago introduced this sort of idea of data-driven discovery, or sort of popularized it. And we hear it, of course, similar themes in many different terminology. Cyber infrastructure, maybe no longer such a popular term, it was really new and hot. In the UK, people like to talk about e-science. We know all these informatics disciplines are very much in that area where we do science using computational resources, big data, data science, of course, a really hot topic. Of course, my affiliation with GISLIS makes me want to talk about information science, digital humanities, and so on as well. So what's going on in this area is that we have often sort of an infrastructure that looks something like this. And this is a slide from a previous project that I was working on in San Diego and then in Davis. So the SEEK project, the Science Environment for Ecological Knowledge, really is about sharing data. So it sounds familiar. So we have data sets, we have metadata, ecological data, in particular specimen collections, and then we need an analysis library. We need tools to really work with this data and have the scientists do something cool with it. So I call this sort of the underwear. And at the top, really, to tie all these things together, there are these scientific workflow systems. And again, here I know in-house, there have been quite a few developed. So in some sense, I guess I'm preaching to the choir. So you see data and metadata going in, being cleaned, being worked with, analyzed, and scientific results come out. Now, what's the problem with this? So this is a conceptual workflow, not yet executable at this stage, of a bioinformatics project in Davis. And you see that it's complicated. Life can be complicated. There's a lot of algorithms and methods and tools that need to be stitched together. And there are all kind of, sort of software engineering challenges, practical challenges to get access to the resources and so on. So the idea in this movement of scientific workflows really try to, facilitate putting these things together. So it's about automating these complex workflows. Also, in recent years, it has been become rather important to explain the results, provenance, and I'll speak to that. So, integration technologies for existing tools, have been somewhat crude, and so the idea was, well, do we really have to stitch it together with our sort of shell scripts? Is that a good idea? Again, there's going to be a life cycle there too. Was a good idea then. We thought, scientific workflows really facilitate that. But it is still a good idea. Yeah, these tools are good at plumbing things together. Duct tape is good, and these staplers as well. So let me summarize a little bit in an acronym what scientific workflows are about. So the acronym, again, I like coining these terms. I call ASAP. So it's about automation, right? We want to automate computational aspects of science. We put together pipelines, computational pipelines. But we also want to scale it up. So many things run on our laptop, and those get more powerful, but we also want to make use of powerful resources, supercomputers, cloud computing, and so on. They should handle large data. So we want to sort of exploit and use machine cycles. Something that's often overlooked, and there's a particular interest of mine, is human cycles. Those are the expensive ones. They don't get cheaper. If only they get more expensive. So we need to actually facilitate tools that allow us to abstract and evolve and share these artifacts, these scripts, these workflows, whatever we're going to call them. So this needs to be done. And then provenance, the P in ASAP stands for provenance, and this is also a very common now and popular theme that we want our experiments to be reproducible. We need to explain the results. We want to be transparent about it, and so on. So let me run through a couple of examples quickly. You see there's a plethora of workflow systems that have been developed over time. I actually didn't quickly find an icon for the systems developed here, and I don't actually know what exactly NCSA is doing right now in this front, but I'd like to talk more about that with you guys here. So here's an example of a bioinformatics workflow that was done by Amber Hartman, conceptually done by Amber Hartman, a former PhD student at the Eisen Lab, Jonathan Eisen at UC Davis at the Genome Center. And she was working with somebody in my group, a computer scientist, to actually make that workflow executable. Okay, so there is a little bit of a problem because ultimately we want to go where the scientists can help themselves. But for the time being, even using a scientific workflow system, it took a workflow expert to really put that workflow together with, a sort of a team effort between the biologist and the computer scientist. And we automated it in this way, and it was available as a tool, downloadable, and so on. There are other workflow examples that we worked on over the years. Here's a small one where a scientist, again, a bioinformatics workflow has a MATLAB script. They ran into scalability issues, and one thing we did was say, okay, let's see, do we have some tools within the Kepler workflow system that we could use here? And then a student of mine, Sven Köhler, then implemented this functionality of that workflow, and then using Kepler, and then using a MapReduce framework that was developed at UC San Diego. So it's a nice thing, of course, with open source. It's a give and take. You can use the tools that other people have developed for you. Just to show some other features of the Kepler system, the underlying computation model, which it inherits from Ptolemy, is really a sort of a stream-based data flow model, and it's therefore rather natural also to work, do stream analysis with it. This is from my colleague Matt Jones at NC's in Santa Barbara. An example how you can use Kepler to stitch together, for example, different R scripts, you see the typical, computational pipelines where data goes in. There are certain switches and parameters, and then R scripts are being invoked. And the whole workflow itself becomes now an interesting knowledge artifact because now it tells you what is the computational method, right? So in some sense, sometimes people call this prescriptive provenance, which is a strange term, but it is basically prescribing what the procedure or protocol was that will produce the data. And the conventional provenance we think of as retrospective provenance, where we look back and try to understand what has happened in our computation. So that sounds all good. So scientific workflows, a silver bullet, we should all do it more and go on with our lives because we save all this time. But there's something known as the Turing tar pit, and you should be aware of it. The Turing tar pit is the place where everything is possible, but nothing of interest is easy. And so if you're not careful, you might end up like these mammoths there and get stuck. So what we found over the years is, of course, that although scientific workflows in some sense have been promising, have been used, and have their place, there are also really challenges with using them. And for example, one thing that first appeals to many people is the graphical user interface. They say, oh, well, let's just plug it together and it's all good. And it's not that silver bullet. There are issues. The things don't fit together. Things can get very complicated. And so along those lines, my interest is basically in optimizing not just machine cycles, which we do in computer science all the time, but also really looking at human cycles. How do we make those things easier? So it's a complicated relationship between humans and machines. If you have seen this series, you know what I'm talking about. Again, in traditional computer science, we focus on optimization of algorithms and we exploit machine cycles. We use parallelism in a big way. But again, the most expensive resource of all is, of course, our own time. And in Bernie's talk, I think, was it last week or 2 weeks ago now, he mentioned also big data is not just about the volumes, of course, also about the volume, but also about big problems with data, period. Yeah. And so, so I'm echoing that. And so from my point of view, sort of slightly philosophically, it's not either one or the other. It's really better together. And spoiler alert, Battlestar, there's some ending that goes along those lines. Okay, so my research over the years has been therefore in scientific workflows at different levels. At the highest level, we have these workflow designs that we're trying to make more beautiful, more useful, more reusable. So these linear pipelines, we're sort of proud of that. And then let the system parallelize it under the hood using some knowledge that we use when declaring these workflows. Provenance, the thing under the hood, is of course what later can tell us what happened. We can use this for debugging, for profiling, for explaining things, and so on. And then along the way, we can also do some traditional sort of optimization of the execution. To give you some concrete example, here's a workflow developed a couple of years ago by my then postdoc Norbert Podorski, who is at Oak Ridge now, in a collaboration with plasma physicists that simulate these reactors. And we ended up with rather complex workflows. And this is a well-designed workflow, okay? So this is not a badly designed workflow. We had lots of those in the beginning. Our first workflows, some of them are in the early papers. I use them sometimes to point out all the bad things that you can make. So this is a well-designed workflow, but it still has some challenges. You see there's, the good thing here is it has these parallel pipelines, so there's really sort of task parallelism. Inside of them there's sort of streaming, so pipeline parallelism, but it is complicated to put these things together. You see it also, other people have been picking this up for HPC. So this is a group that used it for, I don't actually know what their particular science use case here is, but it is also a simulation, computational science, where you use the workflow basically to steer the computation, to monitor. So you have these big jobs running, but you need to interact with them, and that's also what happened here. Yeah? So the workflow does not do the heavy lifting. The heavy lifting happens, of course, dedicated on the machine, but how do you manage these runs? And that's where the workflow technology comes in, and we've used that successfully there. But the problem, again, you see this here already, it might actually be not so much fun to have a Boolean switch in a workflow. Yeah, so there's sort of a broken sort of abstraction levels here. So on the one hand, we want this high-level storytelling. Workflow design should be a little bit more like storytelling, less like feel like low-level plumbing and programming. But at the same time, the systems that we use sometimes have very sort of complicated things in there. And so here's where I get slightly philosophical. So this is a quote from Wittgenstein. Die Grenzen meiner Sprachen bedeuten die Grenzen meiner Welt, which is roughly the limits of my language are basically the limits of my world, what I can think. And we know this from programming languages. So for example, if I grew up in high school with BASIC, and it was a revelation to be able to assign sort of complex variables to one another. Like in Pascal, you could assign one matrix to another. Unheard of. You need a loop for that, right? You need to copy the variables and all of that. So, but that's, of course, you're having the wrong thoughts. In BASIC, you're limited by the way you think about it. Fortran, Algo, Java, Python, all these languages have different ways of looking at the world. So I've been sort of worked on, intrigued by that and working on that in the scientific workflow realm as well. So the underlying model that Ptolemy gave us for Kepler, for example, is what I'd like to call vanilla process network. And if everything is at the same level, then things get quite messy. On the other hand, you might think of the world as maybe as a functional program. Functional programming gurus, maybe some of you in here will notice that things are really fun and higher level and very reusable if you speak that paradigm, if you think in terms of that. If you're in the database community, you might think of XML transformations, and that's how you think about the world. And so we've taken these different sort of paradigms together and tried to distill something that makes our workflow designs better, so we can save those human cycles. And at the bottom, sort of, you see a little bit with the color coding, we have some sort of hybrid of XML transformations and this functional style, leading to workflows that are very linear in their design, but that have enough information so that the system can parallelize its execution. So they're both sort of, we can stitch things together, storytelling style, and at the same time, the low-level details can be figured out by the system. So this, in some sense, was a reaction to the problem of what has been called shims, or adapters between components. All of us who put together existing tools know that at the seams things break, right? We need to write data managing, massaging steps and deal with API differences. This happens all the time in programming. In workflows, of course, it shouldn't be so much there because the building blocks hopefully are well designed, have good interfaces. So shims are a nuisance, and that's why we developed this COMAT. So I'll give a little bit of a high-level idea of how this COMAT works. It uses the idea of child labor. Oh, no, I mean the idea of assembly lines as a metaphor. And so the idea is that we have a data stream that goes through a computational step, and then we configure the actor, the step, the module, to pick up only the relevant items. So just like when you work on an assembly belt, a conveyor belt, hopefully you don't, but if you do, there's things that you don't care about and other things that you do care about that you work on. And so in this way, everybody gets to see everything and simplifies the overall process, and you have pipeline parallelism. So we applied that in Kepler. The resulting paradigm language was called COMAT, Collection-Oriented Modeling and Design. There's a variant of that, VDAL, Virtual Data Assembly Lines. And again, I don't want to go into the details. I just want to point out that there is, in fact, some research, some interesting optimizations that you can do also in terms of parallel processing there. Yeah? So you basically, the incoming stream is sort of parsed out, and then you can do sort of, don't want to call it map reduce, but some sort of simple data parallelism that you can then take advantage of. Also, the designs that you get are not only aesthetically more pleasing, they're more reusable and sometimes even more flexible. So this is a simple workflow that was used in this first Provenance challenge a couple of years ago, where the community started to get organized to work on a shared model of provenance. And this workflow on the top and the workflow on the bottom, they implement the same functionality, only that the one on the top, on the bottom is simpler and more general. So on the top, there's basically 4 data sets that are wired together. The bottom one is sort of collection-oriented. It has these configurable parameters, essentially XPath expressions, tags that allow you what is this vector working on, and then they click together much nicer. It's the high-level idea. Here's another example from sort of again a HPC kind of monitoring workflow. And again, this is done by somebody with a lot of expertise in Kepler and working one-on-one very closely with a simulation scientist, and still is somewhat complicated. And then with this new design that was done by a PhD student of mine in Davis, we get sort of simpler designs and thus more reusable. There's some secret sauce under the hood. I only want to briefly allude to it. But again, the key idea is here that we have sort of a linear data flow, and then we use some structural information, something like XML DTDs, to sort of analyze what's going on. And then out of that linear pipeline, that's sort of serial in flavor, that has a little bit pipeline parallelism, we can do some sort of real parallelism. This is, by the way, I didn't know until I was there in Barcelona. There's a subway station called Parallel, and they have these very nice parallel designs on the wall. So we applied this idea, and in a new approach that we call X-Scissor for XML cut, ship, and reassemble. And basically, we use sort of static analysis methods to chop up the data stream and then fast forward certain items that we don't need. So unlike in a real conveyor belt where you can't chop up the products, but in a data pipeline, of course, you can chop up the data and sort of fast forward certain things. So there's interesting things to sort of speed up these pipelines. There's also techniques like futures and promises that some of you probably are familiar with that are related to this. Okay. So this is a little bit of the research, the scientific workflow itself as a research topic. I think I'll skip forward just pointing out that the life is complicated sometimes. So there are a lot of computation models. Our workflow system here, Kepler, is somewhere up there, or is it? Yeah, well, in some sense it is because of process networks, SDF, and DAG kind of computation models. So these are different models of execution. When you draw this graph, this intuitive graph, it's not at all clear how you execute it. There's lots of possibilities. And indeed, the different scientific workflow systems make different choices, that they have different implications for how parallel can you execute it. How much can you automatically parallelize? How serial is the execution? So one of my students looked at these different models and evaluated them and compared them. And so it is a little messy, but you need to go to this level if you really want to make it easy for the workflows to be automatable, easy to reuse, and hopefully efficiently running. Now let me switch over to provenance topic, and of course that's been a really big topic in e-science, this theme of reproducible science, also in computer science itself, in database theory, for example. So an example to illustrate what the problem is of course climate science is sometimes controversial in some circles, and you want to lay open what the data was that you used, what were the tools. So this is the key idea of provenance, of course, to provide transparent access, or to be transparent about what you've done. And so scientific workflows, in fact, provide a wonderful mechanism here, because they are a controlled environment in which you can sort of tap in and look at the data that flows in and out. You know what code is being executed. You can keep track of all of that. So in the old model, you had a report, maybe some pointers, maybe to data sets, but not a lot. And now we want to sort of break down this wall and really make access to these workflows themselves, but also to the runs and to the data lineage, the dependencies possible. This is part of a larger data lifecycle. This is from the Data One project. I don't know who made the nice cartoons in there. So I haven't given the provenance of this picture. I should have. So the bigger story is, of course, it's not just about executing the script, executing the workflow. There's a whole larger story to it that includes, for example, data curation, preservation, and so on. Topics that are, I think, important, increasingly important, and recognized for their importance. So this can make you dizzy. Do you want to see it again? This is from the Data Curation Center in the UK, in the still UK maybe. And it's complicated, and I noticed rather recently an uncanny resemblance to the Eye of Jupiter, okay? So I don't know. So either some curation folks have been fans of Battlestar Galactica, but it's this vision thing, right? It's just a big, complicated picture, but it is still important to have a vision, right? So that you keep moving, with your gradient sort of in the right direction. Okay. So what are common use cases of provenance data in the sciences? Of course, you want to have an audit trail. Attribution is a big topic. You want to be able to know when your data is being cited, being used by others. You can use it for data quality, because you know what happened when your data was produced. You can then say something more definite about the quality of the data. Helps data discovery, because maybe you want to find data that's only has been produced using certain methods or protocols that you trust, and so on. Again, the topic of replication, repetition, and so on, there's different flavors to this. They all lead into this theme of reproducible science, which, again, is popular. So as a vision, or sometimes already today a reality, we have things like an executable paper, where today you have a scientific publication where not only there's the text that's very human-friendly, hopefully, but also you have pointers to the data, to the protocols, and sometimes the paper itself, certain parts of the paper can be executed automatically. You might have seen, for example, in addition to this, my colleague Juliana Freire of Wistrail's fame, among other things, they have such nice papers that you click on the particular part of the paper, and then the figures recreated. There are many other solutions nowadays in the world of R and Python and so on as well. Okay, so what is the motivation of some of this work in provenance? The typical use case would be that one scientist, say Alice, executes a workflow, and then she wants to share the results with another scientist, Bob. Often the provenance gets lost along the way of that sharing. Yeah? So while we have workflow systems that track individual provenance at the fine-grained level, when we run workflows or when we run scripts, if we have sort of provenance-enabled scripts, Then we publish it, then somebody else grabs it, maybe does something with it, and then goes on. So the chain is broken there. So that's a problem. And for example, the use of Provenance standards to some extent can help there. And this is something we've worked on in the Data One project, in particular in the Provenance working group, to work both on standards and tools to achieve this. So here's a little sort of, again, scenario demo. So we have Alice here. She uses, I think, an early generation phone with an antenna. And so she runs, in this case, a Vistrails workflow through a workflow engine. There are other tools, reproducible, again, developed by at NYU by that group, to package up also parts of the runtime environment. You can't package everything. You can't package blue waters easily. So there are sort of challenges with reproducing everything. So maybe you need to sort of skip over certain parts. That's an interesting research challenge right there. Then there are tools to explore the provenance, querying graphs. Graph databases, of course, a big topic. More and more people have lots of graphs to analyze, of course, in social network analysis, but also in provenance. So in Data One, in that project, we have developed a prototype that would allow you to package this all up. And then later, when you do a search on the Data One infrastructure, then another scientist, Bob or Charlie, I forgot who now, can unpack that and reproduce it, and also see, on the one hand, see how the data was produced in the first place, but also now modify it and use it for his own purposes. And then to produce, in this case, for example, climate science comparison data product there. Okay, so related to the topic of workflows and provenance is really, of course, then the bigger story that I mentioned, the data lifecycle and data curation. And so I want to briefly mention a project called Filtered Push, a collaboration with colleagues at Harvard, where we try to deal with data quality issues that are common in the biodiversity museums community. Literally, sometimes their data is all over the map. So when they collect specimen in the field, those observations eventually make it into records, Darwin Core archives, and certain sort of data formats. And then sometimes you find data quality issues. You try to work with this data. You find, for example, that maybe latitude and longitude have been flipped over. And you see that. That's why the data, certain objects have been sort of collected, specimens have been collected in places that just don't make sense. Maybe they've been collected in years or times of a year that don't make sense because it's all frozen, and how could they have picked up that flowering plant at that time? Things like that we want to detect. This is the very big picture of that project, the way I like to think of it. Essentially, there's the community basically finds data quality issues by using data, say, on the web. And what we like to do is we want to push it back to the source. So we find this data quality issue, so we make an annotation, and then this annotation is fed back into the system, eventually ends up on the desk of the person who has the data problem in their database, and then can make that change. Sort of that's the high-level story there. And then we can also use curation workflows, a special kind of scientific workflows, as a central component there. So we developed a first prototype based on Kepler. We call it Curator or Curation 1.0. We use this workflow design principle that you see, the COMAT design, the sort of linear pipeline, to make things simple. So this would be an example. Maybe in the beginning you have, so this is an executable workflow. It's not just slideware. And we have, say, a CSV file going in, a simple data file going in. And then we have a couple of services that we apply. They can be local, they can be remote. For example, georeference data, we want to validate whether the georeference data makes sense, place names versus lat long. Is it consistent? We look up scientific names. Are the scientific names of the specimen recognized? Which ones are they? Do they need some cleanup? And so on. Now, humans, coming back to my theme, human and machines, we humans become subservient, I guess, to the machine here, because human curators need often to really work with the data when the system can't figure out, this seems inconsistent. There's a duplicate record, but they don't agree. There's only so much that these data cleaning and quality control actors can do. So what we've done there is we've basically put humans in the loop there, and so using cloud infrastructure, kind of cheap at the time there. Just use some free Google services. So this doesn't scale very well. But we basically put the data as sort of a Google sheet out there, and then send email to the curator pointing them to the data set and say, look, this is what the workflow produced. Here is color-coded, highlighted, the old value, the new value. This is what we think it should be. Please fix it. Hit the submit button on the spreadsheet, which is kind of nice that you can do this in the cloud. And then that feeds back into the workflow. Yeah? And then in the end, you get your cleaned up, so both machine and human curated data out there. And then, of course, you don't trust it. Yeah? So then you say, oh, wait a minute. This went through these automatic steps, and then some people had their fingers on. That's, of course, where you need the provenance. Yeah? So on the lower right, you see after the data has been cleaned, put on the map, everything is good, but we also have a record of the provenance of the lineage that shows how we arrived at the data. So if you question the quality, or if you just want to look at it, you can then do that. Yeah? Okay, so I don't want to go too much into the details, but again, this was the key idea. We use sort of a Kepler workflow, but then we use calls out to the cloud to make it all happen. The particular component was then, for example, an actor called Spreadsheet Importer. It has all of these ports, so we do need to go to the lower level plumbing sometimes again. And then, so here's sort of a couple of screenshots that show you how it looks like. You get the mail, you're being asked to look at the spreadsheet, which you then do. You look at the values, you see whether, hopefully you're the right expert for that species or for that taxon there. And you can then make changes, and then eventually hit the submit button. Let me see whether I can find it here. So there should be somewhere here. Okay, I don't see it right now. So there's in the spreadsheet, there's a button that allows you to submit this. Again, it goes back in the workflow, and then again, you get the final result back. One of the challenges we found in this project was to explain the provenance to the user. So these graphs, they scale only so much, and they're sort of tedious to work with, unless you have really good viz tools. That somebody here in the audience is a sort of a graph viz expert or guru. I'd like to talk to you how we can better visualize and query provenance graphs. One thing that I think is more helpful sometimes is just use basically spreadsheets and color coding, and then allow people to click on that and look at that. All right. I think I want to just briefly mention a couple of other uses of workflow technology and provenance. For example, here in the Data One project, where we are working with a team also of people doing climate science. Which is, of course, a very good use case. I mentioned it earlier in the motivation. So let me just mention here. So this is this tool called Vistrails, and the particular sort of incarnation of it or elaboration of it called UVCDAT, and that has been used, successfully for these climate workflows. Now, then there's one more thing. There's actually a lot of more things, so I'll skip over them briefly, so I can, both summarize with decent speed and then have you guys all have some snacks outside. Okay, so one problem with provenance is, like in all kinds of data issues, there's so many models. Yeah, even ontologies were used to mean a shared understanding of a domain, and then everybody makes their own ontology, and then you start mapping between ontologies. You get the old mess again. So the problems don't go away necessarily, in particular if you have many standards. So there has been, out of the community, there were two standards. Basically, there was this open provenance model, OPM, that came out of sort of this grassroots community effort, and then it was reworked and got blessings, W3C blessings, and is now called Prov. But still people find reasons to extend that model, right? For example, in our case, we said, okay, the Prov model by design is a very generic model of provenance. It just captures what goes in and out of a computational step and tries to be minimalistic by design. But then when you do workflows, there's all these different levels of things going on, right? There's what we call workflow land. There's the high-level workflow story, the workflow script, if you like. And then there's these lower-level executions. There are invocations of services. There's all these different levels of things going on. How do we put that into that simple generic model? In fact, you can put it in there in many different ways. Just like you have many ways to design a database, different schemas. You can have different DTDs. You can, just that you use an OWL ontology doesn't mean that you agree with somebody else who also uses an OWL ontology and does a very different job. So we have all these issues. So we tried also through a community effort to arrive at the extension of Prov that we call Prov1, as in data 1, that sort of synthesizes and brings together ideas of other approaches. So why is this story a little bit complicated with workflows? Again, here's a model how you can think of a workflow at the highest level. There's computational steps, these green actors. There's data containers. That's how I like to think of them, folders in practical workflows that people do. They don't call them workflows, they call them scripts, right? You work with folders, you organize them into subfolders. You have naming conventions. This is good stuff, actually. So this model tries to fit that as well. But then at runtime, you have instances of that, right? Batch processing, which I started with, batch processing is doing the same things over and over again, but you need to keep those different versions, separate to tell the whole story. So we've been working on models that sort of faithfully sort of deal with workflow land and trace land, the actual run, sort of provenance, runtime provenance, link that together, and it turns out there's interesting research questions as well. So people would normally say, well, it's just a graph, go on, what do you want? But there are very interesting logical and temporal sort of intricacies to be considered, and I'm happy to talk more at some other point with you about that. It's hard to get across in a very short time. Okay, so we've built some tools that basically analyze the different kinds of provenance. So this is alluded here also, the sort of different abstractions of your workflow, different runtime models. Let me maybe give you one example of that, a concrete example. So there's these Hamming numbers that have been known since the old Babylonians. They've used them, and they're also a popular programming exercise. Dijkstra, Edgar Dijkstra, of computer science fame, has also one of his notes on that. So what you want to produce is you want to produce an increasing sequence of numbers to multiples of 2, 3, and 5. And I assign that to you all as a programming homework, over the weekend. Those of you who program, please write a program in your favorite programming language. Doesn't matter what it is. Pick one, and then produce in increasing sequence the multiples of 2, 3, and 5. And I'll tell you also what you cannot do. You can't just have, say, a for loop or a while loop that enumerates the numbers and then checks whether the number is divisible by 2, 3, and 5. And if it's only divisible by 2, 3, and 5, then you output it. That's cheating, right? Because you use division. We're supposed to multiply these things together, and then only generate the right ones and then output them in order. Now, it turns out that's kind of both a simple problem and actually not so easy to program. So it goes back to this, how do you think about a problem? What is your sort of language of choice? What are the concepts? So it turns out it's very simple if you think in data flow. If you have a data flow system, sort of a pipeline, in this case with a feedback loop, it's beautiful, it's easy, it's simple. If you think of it any other way, it gets messy. So this Kepler workflow here, or this data flow pipeline, will compute it. Basically, the key idea is you start somewhere with the number 1. For certain reasons, we start I think here with the number 1, and then you basically loop back, and you have these multipliers. You multiply with 2, 3, and 5 in all possible ways, and then you have these merge steps that basically maintain queues and pick always the smaller one, and that way they come out in order. And this goes on basically forever, or until you run out of memory or time. Now here's an interesting question. You can do it in different ways. So the data flow network on the left and the data flow network on the right both produce the same sequence. Which one's better? Or, it's not obvious how they work. But as a high level, you might see the feedback loop there, sort of branches in 3 parallel branches, but the structure here on the right is a little bit more complicated. You see here that you have a little loop up here, and then you have another larger loop here, and then a third loop. So these loops are somehow, in some weird way, nested. Whereas here you have sort of one big loop with 3 parallel branches. So where does provenance come into the picture here? If you look at the provenance, it is very easy to see which one of them is more efficient. You wouldn't see this from here. So we found applications of using provenance, not just for the usual sort of purposes of explaining how you arrived at a result, but also for internally, for example, for debugging and for profiling different workflows. So sort of a related quiz is if you have a trace, was it this workflow that generated or was it that? Again, the output is essentially the same. Once you look at the provenance, you see a big difference. I call these two provenance traces, I call them the fish and the sail for obvious reasons. The fish has many more edges, and each edge is a multiplication. So you did much more work there. The sail is a tree. Every number is produced once. So the big difference, what's happening is one of these data flow networks creates lots of duplicates that you then have to remove. So first you create them, then you filter them out. The other one, because it's sort of clever design, doesn't even generate the duplicate in the first place. Yeah? So that's sort of interesting how, first of all, a data flow network is actually the right paradigm in which you should model this sort of infinite process, and then how you can use provenance to figure out sort of between different variants which one is sort of the better one. Now I'm coming close to the end, and so I will not talk, but will advertise again some other talks that I'm going to give that are rather different. So I have a project that's a lot of fun working with a colleague at Arizona State who is a weevils expert, so these beetles with a long snout, or whatever that's called. So he knows all about them. He's probably one of very few people in the world who know all about them. But he uses another tool that I've been working on with my students to do alignment and then reconciliation, if you like, of different taxonomic perspectives on the world. So you have two taxonomies, expert articulations between them, and now you need to figure out, is that even consistent, and is it ambiguous, and how do you deal with that? So it's a rather different kind of work, and I'll skip over a couple of other things. Maybe just want to mention one current other project, the Data One project that I'm involved with, is working with climate scientists that do a model comparison, and that's a wonderful opportunity to do provenance research there. So what these guys are doing, they already sort of integrate different simulations about climate science, and then they try to benchmark them, compare them. And in order to do that, the data has to be comparable. And so they need to do some sort of data wrangling, data cleaning. They use scripts for that. We want to capture the provenance of those scripts. They actually classify. So this is not a biological classification here that you see on the right. Where is it? This is actually their classification of the models themselves, right? So they try to compare climate models with one another, what parameters are, and units and what quantities are being included and not included. And yeah, so that's an exciting project to be involved with. Let me start closing down here with sort of a, again, slightly philosophical perspective here. When we started out with developing scientific workflows and many others of cyber infrastructure, I think, activities, we always want to build tools for the users. Yeah, say, hey, let's build a good tool for the user, put it in a web interface, and so it's easy for them to use. What that fails to address is that users sometimes want to be more powerful. If you see that guy up there, it's a movie. Another movie buffs will hopefully know what that is. It's from 2001. We'd like to be tool makers, so we should not. I think that's maybe also a general advice, maybe that for people here at a place like the Supercomputer Center or GISLIS, other places, we should try to empower users to make their own tools. It's a whole different sort of world that will be available to them. I mean, led to us, yeah, evolution. So, for example, one tool that gets a lot of uptake in many areas is, for example, IPython, and there are other sort of similar efforts, for example, for R, which are these digital notebooks in which you can basically sort of a little bit of a reinvention, or not a reinvention, but a sort of a new incarnation, an evolution of an idea like literate programming, right? We know literate programming where you write code, so you say what you mean. Excuse me, you write in English what you mean, but then you write code with it, and it's all integrated, right? And it's actually similar to this idea of the executable paper, that you have human documentation and the code next to one another. It's all transparent. You can share it with others. Getting a lot of mileage recently, this, and growing a lot of legs. So you can do, you're really empowered to make your own tools. I just looked at this recently. I tried to make a screen capture of a Python notebook, and it had sort of JavaScript, sort of a D3 animation in it. Gives it an all new sense of what screen capture means, because I tried to capture that. And that thing is so interactive, it sort of was wiggling out of the focus all the time. So you might know some of these animations when you move the mouse there. I mean, this is dead now. I froze it. I captured it. But if you move the mouse there, these things go all the way. So you have a very interactive environment that looks very much like you would write text, but then you have intermingled code, and it's getting a lot of attention. So this is being used, for example, I found this just recently in the context of data curation and astrophysical data, of all things, that I thought was an interesting combination. Data-driven journalism, and in fact, this whole idea of reproducible academic publications, the executable paper or scientific workflows and provenance together is taking on a whole new meaning and a whole new life in this environment. So it's very exciting to also start working with that. All right, the conclusion. Better together, and again, you might just barely make out what that thing up there is. That's Hera and her parents, for those of you that know. So I try to give an overview of the kind of work I've been doing and continue to be doing in the area of scientific workflows. I care about both human and machine cycles, so I'm interested in optimizing workflows, but I'm also interested in making it easier for scientists to put these things together. And that might require sometimes really sort of complicated digressions, say, into computer science topics. So better together also means theory and practice should go together more. It's sort of also maybe a general recommendation that I can give. Often people fall into these different classes, experimentalists and theorists and practitioners. They all like to sort themselves out taxonomically, but we have more and more overlap really happening, and we need to foster that. In my own projects, I do sometimes things and have a lot of fun with it, where I apply computer science problems using some sort of weird logic formalism called answer set programming, and then I use information visualization using graph viz, all actually very simple, and I get really nice results, and I can do this with undergraduate students. So if you put the right things together, you can actually combine theory and practice in new powerful ways. I'll just mention software carpentry is some of you will know, a very popular sort of workshop series that's touring the country. And there are sort of also spin-offs that focus more on data carpentry. Again, the idea is to empower people who are not trained originally. They're not computer scientists, but they may be biologists, for example, or they could be library scientists, information scientists, to get their hands dirty and empower them to make their own tools, or use sort of very open tools to get the work done, and allow them really to go to the next level in their evolution. Okay. So, and I think that, I'm very excited to be here. I'm at GISLIS, which is already a very sort of collaborative and interdisciplinary place, and NCSA as well. Of course, all the sciences are coming together here. I also have a leg in computer science that I like still to do. So I'm really excited to be here, and looking forward to working with hopefully many of you. Thanks.
So we'll take a couple of questions. If you have a question, please come to one of the microphones so those that are remote can hear what you've asked. Questions from anyone? Well, of course, I've got to come prepared with one. So what I was looking for is where are the direct connections in a Kepler workflow? It wasn't clear how I'm providing the information that provides the provenance to the data. Is that automatically being collected, or do I have to provide something into the workflow for it to be possible to be collected?
Yeah, so I glossed over a lot of details, and I think I have this habit of spanning a lot of wide area here. In Kepler, this is actually interesting. I should say Kepler has different execution models, first of all. So you can put these, what are called directors, which we inherited really from Ptolemy. You could put them on the canvas, and then that graph executes differently. In some sense, sometimes you should actually know something about the computation model, or the model of computation, in order to capture the right provenance. The very particular question that you were asking, there is a default provenance recorder that you can enable that was developed in San Diego that would automatically basically monitor the ports. So as data goes in and out of a step, this data is being recorded. So references or values that go through the workflow. And then they're put in a database, and then they disappear forever. No? So a challenge there is that with provenance capture in general, you might have too much provenance. You might not, you need to make decisions, and that's where the tool might be, improved. There are some mechanisms to sort of fine-tune what gets recorded and what does not get recorded. It's actually a rather different ballgame whether you are sort of in a highly automated workflow, sort of production workflow setting, or whether you're, for example, in a notebook where you sort of exploratory, really put a script together as you go. And those are rather different kinds of provenance. I wasn't really able to go into sort of the different flavors of it, but let me see whether I capture hopefully your answer. So again, it's automatically captured once you switch on the provenance recorder. It goes into a database. What is in there is in some sense the sort of input-output relationships of the data items. And then you can exploit that later to, for example, you could do things like the fish in the sail. You could figure out which provenance graph is it, for example, in this way. Mm-hmm.
So this provenance that is used in creating some reproducible material, but there is a cost of reproducing any result. I mean, how do they manage this, in terms of actually trying to say something is reproducible or not?
Yeah. So, and again, I glossed over a lot of things here. I should maybe say, not all provenance is really meant to really allow you to automatically, for example, rerun a workflow. Yeah? This sort of recomputation, that's a slightly sort of different use of it. And cost that you mentioned is a big issue. So experience showed that in some of the workflows, there would be a considerable overhead if you write out all of this provenance information. I mean, if you are a simulation scientist and you write out checkpoints from time to time because you might want to restart a simulation so you don't lose all the time up front, you know how expensive this is and how careful you have to be where you put those checkpoints. So I think there's currently not a lot of convenient support for really fine-tuning this. What is it that you want to record or not? And again, I think we need better sort of formalisms, better tools, I think also. People in practice, they instrument their own code sometimes. They just literally write out, in the old days, you would write out a checkpoint of your program, and then you're under control of how much you want to do. But there can be significant overhead, and so sometimes you might just not record provenance at all, or in certain stages of the process. The provenance, depending on what you store, can be bigger than the original data, and then you already have problems with your original data. So it can be prohibitively expensive in certain cases.
Other questions? Okay, well, let's thank our speaker one more time.
Okay, thanks. And,